The following is a segment from our webinar entitled HVAC Right Sizing Part 3, Air Distribution and Duct Design. It was presented by Arlen Burdick and Anthony Grizzolia of IBACOS through our Best Practices Research Alliance. For further segments and other video materials, visit our YouTube channel at IBACOS and the Alliance. This segment features performance criteria and design principles as they relate to HVAC duct design.
Performance criteria that we're looking for as we go through this. Temperature uniformity. We want to look at how that air is delivered to the room, and noise is actually a comfort criteria that needs to be considered. Temperature in the room is maintained by delivering that air to the room so that it can mix with the room air that's there, get a nice even temperature. We want to deliver that air in a manner that does not create a draft. A draft is a perceived draft is a comfort issue. Proper mixing helps avoid stratification in the room where you have hot spots at the top and cold spots at the bottom. Room-to-room variations. Up to 2 degrees is desirable. ACA standards say up to 4 degrees is allowable. How do you avoid that sensation of a draft? You have to consider the occupied zone of the room. 2 feet off the walls, 6 feet off the floor, where the typical person would be in that room. Keeping an eye on the velocity, the terminal velocity of that air that's entering the room, and making sure that it mixes properly. Again, all these are concepts we'll get into deeper as we go along.
All right, I have one question here. A lot of times when we work with builders, majority of the time, building officials see, a supply register needs to be accompanied by a return register in the same room to circulate that air in that occupied zone. How do we combat that with some of our building officials when they want to see those scenarios?
We're going to talk a lot about the importance of return air strategies later, but there has to be an understanding of how the system works, and it really is comprehensive. It's not one point after another. Noise is definitely a comfort issue. The images on the right are return strategies to avoid noise from the blower, but it also impacts on supply. Too high a velocity from supplies, as airspeed increases, so will the noise with the improper sized outlet. If it's leaving at too high of a velocity, you get that undesired whistling noise. And again, equipment placement when you're doing your integrated design will help you with noise issues. Design principles. Again, kind of repeating what we said earlier, but the house with a lower load is going to have less air required to condition it, so smaller equipment's required. The performance of the system is really based on making the best use of that available air, and that's what we're going to talk about in our supply delivery strategies and our return strategies, is getting the most use out of that air. As we talk about designing the system, every item that is in that system, from the blower motor through the heating coil or cooling coil, heat exchanger cooling coil, back through the ductwork, back to the return, back through the filter, that is all makes up the system and needs to be accounted for. That's what I did. Sorry. The material that makes up our ductwork very much impacts the performance of it. Air flowing inside the ductwork is subject to the resistance inside that ductwork. Galvanized steel is smoother than insulated fabric flex ductwork, so that it'll have a smaller, less resistance to it. We see that picture of the 3 90s getting around the floor joist again in the bottom there. Every 90-degree bend can add as much as 35 feet of length to the duct run, even though physically it's only a foot or less. The friction that's added, the resistance that's added by making that air turn that corner adds to the length of the ductwork. Mentioned that flexible ductwork has more resistance than galvanized steel. The way that flexible ductwork is installed also greatly affects the resistance within it. This flexible ductwork comes out of a bag all nicely compressed, good for shipping and putting in the truck. When it gets to the house and is installed, it needs to be fully stretched out to minimize that roughness, those waves inside the ductwork. The picture shows how badly that can be affected based on a percentage of compression. Return air is very important. We at IBACOS, and I think in general, we look to look at the return air first. Maybe a little bit pragmatically, because return air is often neglected, but it is a critical component. But your return air is going to be your largest cross-sectional section of ductwork. It's going to be the biggest piece in the house. You have to think about where that's going to be relative to the rooms to get good return. You want return air to, in quotes, see a clear path from every room that has a supply outlet back to the equipment. The exceptions for return air would be bathrooms and kitchens, and that's due to moisture and odor issues.
Quick question on this one. Why are you saying we need to locate return ducts on the floor plan first before supply ducts?
Mainly for that reason that its location is critical for its performance, and its size really impacts. You could be looking at 14, 16, 18-inch, 20-inch ductwork of space, diameter space, that return ductwork. The reason that return air is so important and that a clear path from every room with a supply is rooms without adequate return air will become pressurized. As the supply air enters the room, if it doesn't have a clear route out for the mixed room air, you will pressurize the room like a balloon, and you can slow down or impede that supply air's path into the room. The classic story about this is mom puts baby down for a nap in the room and closes the door, comes back in and the room is hot. This is a room that wouldn't have a clear way back, utilizing a door undercut or some ineffective method of getting air out. And what has happened is that room has become pressurized, the supply air has slowed down and gone to other places in the house, and the room is heated up, baby wakes up sweaty. We say here in the second bullet point that a direct return from each room is not desirable. It's not the best strategy because you have to account for all that return air ductwork in your duct length as you're calculating your duct system. So what we're going to talk about on the next slide is the use of a central return. No, I've got to talk about this first. As you place your return duct and you size it, sizing is very important. We want to see a very easy path for that air to get back. Some strategies to avoid turbulence in that return air box is to extend the return air duct into the box, avoiding turbulence in the upper part of it that impedes flow back in. I got out of order. Here's where we talk about locating central returns. Central returns are simple, and simple is good. It's already complex enough. The more things we can do to simplify it are better. What's shown on this floor plan is a central return in the central hallway with over-the-door transfers as pressure relief to get the air back out of those rooms and avoid that overpressurization. We don't want to see the use of building cavities to deliver air, but you can use over-door transfers or high-low transfers for return. the cross-sectional view of an overdoor transfer. An overdoor transfer can simply be a hole in the drywall on either side of the wall, inside and outside, with a grill on it. This is showing a more elaborate setup with a baffle. As you open up that area for air to pass through, you also let light and sound pass through. Having the baffle in there is one strategy to avoid that. Another strategy to avoid the light and sound issue is a high-low, simply putting the interior one high and the hallway one low, creating a pressure relief place for that air to go. Or over-the-door transfers, different from a duct run going all the way back to the equipment. An attic transfer duct just allows a place in the ceiling through ductwork for the air to pass from interior to exterior. Selecting the supply outlets is critical to the performance. Like we said it probably 4 or 5 times already, that the air has to be delivered in a way that it will mix with the supply with the room air. The manner in which that air is distributed really depends on the outlet that you've selected, and the placement of that outlet is just as important as the type, where you're going to put it so you get good performance out of it. Few terminology things. Face velocity is the velocity of the air as it leaves. Terminal velocity is the velocity of the air at the end of its effectiveness. Just for scale, 700 to 900 feet per minute as it leaves the supply, 50 to 75 per feet at its terminal velocity. Throw is how far that air can effectively reach out into the room for mixing. Spread is the width of the air as it leaves the outlet. And the Cananda and the Bernoulli effects, that's the science behind why this throwing register approach works, by allowing the low pressure area between the air and the ceiling to carry that air farther into the room. We all like step-by-steps, but this is not sequential, and there's very much back and forth on this. But to select the proper outlet, you're going to want to go to the manufacturer's performance data. They will give you data that tells you how the supply outlet will perform based on the amount of air, the CFM, that's leaving, and the lost my train of thought. the amount of air, the CFM, and the velocity at which that air leaves the supply outlet. They're all typically set up for something like 50 feet per minute terminal velocity or 75 feet. You have to look to see what that manufacturer has put it at. So you're going to scan the data, check the noise level, check the throw and spread, and check the pressure drop. And where do you check that at? It looks something like this. This is the way the manufacturer presents the data to you. The far left-hand column is the size of that register or outlet. The upper row is the face velocity. Pressure loss is very important. You want to know what the pressure loss is at that so you don't exceed the available pressure in your system. This is actually, and then noise criteria, 30 to 35 is typical residential noise criteria, and they will tell you on the chart what the noise criteria of that outlet is. This is a good example of how hard it can be to find a correct outlet. The smallest one this manufacturer has shown us is 8 by 4. And if you're in that 700 to 900 feet per minute we're looking for, that's CFMs in 110 to 145. That's probably more than most rooms in the house are going to require in a high-performance house. The catch here is, because they've listed 8 by 4 as their smallest, doesn't necessarily mean that's the smallest one. You may have to go back to them and ask for more data than what's readily published. Although this is getting better and has been getting better for many years. There are more choices, more variety for us. Don't have to jump to the light commercial register. There's more stuff available in the residential line. a picture's worth 1,000 words, then a couple moving pictures might be worth 10,000 words. The next couple of slides are based off a study that IBACOS did from 98
to 2002.
98 to 2002, where we built this room back in our shop area and set it up with some registers and injected smoke-filled air into the room so we could see how the air performed within the room. I have 3 different scenarios to show you. One is the typical floor register, one is the ceiling register, and one is the high sidewall throwing register. And they're all at 100 CFM, so the same volume of air is being delivered to the room. And I'll back up and show you how that happened again, but you can see the smoke coming up, washing the wall, coming out into the air and mixing with a typical floor register. Comes up, reaches the ceiling, and comes out to fill this portion of the air of the room. In looking at a ceiling register with the same delivery, I should have pointed out where the register is. The ceiling register is over here on the left-hand side of the room. It's not central to the room.
Top left.
Top left. Back up. Show you that one more time. The air is entering here, coming in, hitting the wall, and mixing down here. And the third one is a high sidewall register delivering the same 100 CFM. Show that one more time. So the room is 16 feet in length. These squares are 4x4, 2x4?
I think they're 2 by.
Yeah, so
like
the room is 16 feet in length. So you can see how the air came out, reached this wall. You got this big pool of mixed air out here. Just a kind of an example of how those diffusers work, a visual example of how they work. One more word on placement of diffusers and why maybe a floor diffuser is not the best place. You can't predict where homeowners are going to put furniture or where the dog is going to lay down to take a nap. Floor registers are easily covered up, blocked by furniture placement, which will definitely impact the performance of the system. So in choosing them, you do have to take into mind availability, like we talked about, the sizes that are available. The prices are coming down as they're becoming more common. Material appearance. Like we said before in the previous slide, that residential stuff is becoming more available. It's not so much you have to go to the light commercial like we used to, maybe even 3. So locating ductwork on the plan, very closely related to locating your outlets on the plan. From that early integrated design work and your room-by-room airflows that you got during your manual J load calculations, you roughly know what size ductwork you need to get to which room and where it can go. This portion is where it can go. We're trying to locate our supply outlets as close to the interior of the room as we can. The reason for doing that is to keep our ductwork short, less losses in short ductwork, less heat or cooling losses in short ductwork as well, less surface area to lose capacity through. Looking at the floor plan in general, you'll have a selection between one-way, two-way, and three-way throwing outlets. So you can pick the appropriate one for the room shape and size. Looking at it.
Oops, sorry, that was me trying to fix this. Go ahead.
Looking at the far left-hand circle that's serving that kitchen nook area, it doesn't go straight out off the trunk because there's a trade-off there of keeping the trunk as short as possible versus a little bit of extra supply ductwork going to it. So it comes straight off, jogs to the left slightly, and then out to the area where it's going to perform the best.
Arn, one question that a lot of builders have, if a builder does this approach of locating supply registers interior into the floor plan, is there impact on trades and cost?
Ideally, it would reduce the cost of ductwork because you have less ductwork, and in the effort of always keeping things as simple as possible, their installation should be faster. If this is, and this one happens to be, flex duct coming off there, the less distance it has to travel, the less chance you have for it to be kinked or wrapped up or not get it installed properly. So yes, there should be an impact for them. We would hope. A positive impact, we would hope. This is something that we see everywhere that uses flex ductwork, using the splitter box to get air out to various rooms. The large ductwork coming into the top is the main supply coming from the equipment, and the 6, 7, 8 branching off of it are the supplies going to the room. Lots of questions on this, lots of discussion, not a whole lot of guidance in ACA Manual D on how to handle this. Something we did here at IBACOS just recently in the last 6 months or so. Yep. We created a few CFD models, computational fluid dynamics. Yeah, CFD models to look and see what's happening to the air inside that. So this is a model to replicate that one that we just looked at with the large supply coming in the top and the supplies running out the sides and the end. The color scale is velocity. Really what we're concerned about is CFM, and we have a numeric table if you like looking at numbers more than you like looking at pictures. But this is how that setup performed. There was a 30% variation between the designed CFM and the actual CFM as it was delivered to the rooms. Another way to approach the splitter boxes, and one that we often talk about in the field when we're walking, is bringing the supply into the side, not the top, not bringing any outlets directly in line with the inlet supply, and then creating, if you can see my mouse moving up here in the upper left-hand grade picture there, creating a extension to the end of the splitter box that will create a pillow of air to allow the air to redirect where you want it to go. So in the model, the colored model here, you can see how supply air is coming in, hitting this kind of back pressure pillow here, and then making its way out.
Arn, from this picture, there's a lot of swirly lines here, but which of the supply branches have the best airflow?
The far two outlet ones. And I'm sorry, I don't have a number to line up at the table, but you'll see that in the numeric
so
table.
it's the straight line flows.
Yes. Less energy lost in swirling around inside the ductwork. Here's the table that numerically lays out how that goes. And, the first scenario had a 30% variation from the ideal. This one has a 5% variation ideal overall. This is really the most complex, hardest part of the whole thing. Everything up to here has been kind of not theory, but why you want to do it. When it gets to how you want to do it, we're not going to cover it here. We can't cover it here, but we're going to talk about places where you can get the information to cover it. But in general, there's 4 things that are affecting this. You know, the delivery of the air, the friction loss, not just in the duct but in the whole system, like I spoke. The cross-sectional area of that duct will affect the velocity in there and the average velocity moving in that ductwork. Friction rate is very important. It's the pressure loss between 2 points in the duct system. It can change depending on which duct you're in and where you're at in the duct. It's a very critical component to keep in mind as you're doing this. Effective length and equivalent length. Equivalent length really depends on it's speaking to the fittings. That's that 90-degree elbow that was actually 35 feet as the air saw it. Effective length is when you've combined all those fittings with your straight duct. So these are the 4 variables: duct diameter, flow rate, velocity, and friction rate, that all have to be balanced against each other as you select your ductwork for the layout that you need to get the air to the room. ACA Manual D will calculate that friction rate based on the worst case or critical path, and then that friction rate is used for all the duct runs. It's a critical path, worst case scenario approach to it. ASHRAE 2009 handbook describes how to achieve a self-balancing system, in quotes, by calculating the friction rate of each duct correct for that duct and the fittings that are in there. In this case, software and spreadsheets are truly your friend. It's a lot to keep track of back and forth. We discussed that the higher performing houses do have lower loads, so less air is going to be required to condition them. And early consideration of the HVAC system in the whole house design will help you both in performance and cost. Lower volumes of air must be mixed properly to get that conditioning, so your outlet selection is very important there. Noise must be considered just as much as temperature and draft, and the return air system is critical to the performance of the system. We always have to come back to this one because it's just not step by step, do this, you're done. All the back and forth arrows, the dashed arrows back to blower performance. As you design the system, you're going to run into things that are going to force you to go back and redo until you get it right. And in any case, good design must be followed by good installation. Flex duct, stretched, those kinds of things.